So very good day to everybody once again. This is Algorithms 1, and in this class we discuss about DP, dynamic programming, about the principle of optimality, and finally the coin changing problem. Okay. So this is especially for you, my dear students and young researchers, and you can reach me at dr.christoananth@gmail.com. So before beginning the session, once again let me thank God for giving me this opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students and young researchers. Right. So in this class, we discuss about DP, dynamic programming, and about this example, how actually this dynamic programming works. What is the difference between recursion and then dynamic programming? Then we discuss about optimality principle in network topology. Then we have a sync tree for the router B. Okay, so then we discuss about DAG, directed acyclic graph. Then we move on to the second part of the class, which is the coin changing problem. What is the dynamic programming for the case of Python? And then we have the implementation of the coin change problem. So I had given the enumerant work for you. Please complete them as soon as possible. And at regular intervals, I'll be giving you some short videos to discuss the knowledge in our topics. So this is dynamic programming. Of course, you use it in the computer programming in order to solve a class of problems. Okay, so that will be having overlapping subproblems and maybe optimal substructure property. Okay, so maybe the problem you can divide it into smaller subproblems, and even that also can be subdivided into smaller subproblems. Now the problem is that if they have overlapping subproblems, then the solution you can use it for future use. So through which the efficiency of this CPU can be actually enhanced. So this one you can call it as the dynamic programming. So each of this will be having an optimum solution related to it. So let us find a Fibonacci sequence. Okay, so that we will be considering with the series. Okay, so as you know, with the Fibonacci series, you will have 0, 1. Okay, so this 0 plus 1 you get 1, 1 plus 1 you get 2, 2 plus 1 you get 3. Okay, so every number is the sum of the two preceding numbers. So let us take an algorithms where we have n. The n is nothing but the number of terms. So if the n is less than or equal to 1, you return 1. Else case you return the sum of the two preceding numbers. Okay. We are calculating this Fibonacci sequence up to the fifth term. So this is 1, 2, 3, 4, 5. Okay. So first one you have to initialize to 0. Okay. Second term you know it is 1. So third one you can say that it is the previous two numbers you are going to add on to it. Okay. So the third number, it is nothing but the previous two number additions. Okay. So fourth number, similarly the third term and the second term you are going to add. Fifth term, of course, fourth and third. So that is how you are going to get the sequence. Okay. So this is how you are going to solve the Fibonacci series with the dynamic programming approach. So how this DP is going to work? So here it will be collecting the result from the subproblems, so that whenever the solution is required in the future, we need not have to recalculate it. Okay. So this one you can call it as the memorization technique. Okay. So here you will be having variable m, the map 0 to 0 or maybe 1 to 1 you will be having function Fibonacci. If this key of n is not in the given map, which means that you are going to have fib of n minus 1, which means the previous term and the next one that you are going to add them, and that is actually the current term. Current term is actually m of n, and you return the m of n. So this is the top down approach. Okay, so top down approach, so previous step and the next step that you are going to add, so that is the way you will go with this one. And you can also reverse the direction in which the algorithm is going to work. Okay, so you can start from the base case and work towards a solution, and you can go in the bottom up manner also. Okay, so here you will be having function Fibonacci of n. If n is equal to 0, return 0. Else case you go with the previous fib is equal to 0, current fib is equal to 1. Okay, and you repeat n minus 1 times. So variable new fib is equal to previous fib plus current fib. Previous fib is equal to, now it moves on to current fib. Okay, and current fib is equal to new fib. Okay, and you return the current fib. Okay, so every time you add the numbers, then the current fib and the previous fib, that gets interchanged. Okay. So the dynamic, you can use it in the recursive algorithms even, and you can get the solution of the sub problems that you need not have to save it for future use. So that's what you call to be the memorization technique. Okay, so there's a presence of overlapping sub problems, okay, in the Fibonacci sequence problem, and you can go with the recursion technique. And similarly, if you can go with the merge sorting algorithm also, so that you cannot use a dynamic programming because it's not having a overlapping nature. Okay. Then we compared greedy algorithms with the dynamic programming. So greedy algorithms, it's pretty much similar to the dynamic programming, but they look for, because only possible means of convergence is the finding the local optimum solution. So that is the reason both the greedy algorithm and the dynamic programming look alike. Okay, so similarly, dynamic programming also finds optimal solution to the subproblems, and it will be combining the result of the subproblems in order to find the most optimal solution. Okay. So here is the optimality principle in the network topology. So we'll have, okay, the router J. Okay, so that's finding the optimal path from I to K. So the optimal path from J to K also has the same route. Okay, so maybe you can call a route from I to J R1, and the rest of the route maybe R2. So that one you are going to add the two routes, okay, in order to find the optimal solution. So here we will be considering, okay, a tree called as a sync tree. So here is the tree, you can call it as a sync tree. The distance is nothing but the number of hops, and you have to find out the cost of the tree that is associated. Okay, so the goal is to discover and maybe use the sync tree for all the given routers, maybe from A to B, B to C, C to J, that you have to find out. Okay. So maybe a sync tree for router B. Okay, so this is the thing. Okay, from B you are going to reach out to each of the nodes. Okay, B to A to F, F to K, K to L. So this is how it goes. So in order to find the optimal solution, we have to find out the distance that is associated. For example, let us take in the case, this is 2, this is 2, this is 3, this is 4. Okay, so here it will be calculating the distance of the tree. Okay, from B to L, this is the optimal solution. Maybe here if it goes 1, okay, maybe A to D it will go, D to G it goes, then G to L, maybe there is a connection. So maybe if there is a connection, and if it is having very less hop, so which means that that is the optimal solution. In this case we cannot do it because there is no connection, and you should take only this path because there is no other connections. Maybe if there is connection between H to L, and if the cost of the nodes are less, then we can choose that particular convenient, also less number of hops. Okay, so the sync tree is not unique with the same path even, and we'll be having, you know, a directed acyclic graph even, where it will be having no loops, so it will be going straight in a linear fashion. Okay, so here we'll be using sync trees for the convenient method. Okay, so as to avoid this traffic or maybe any unwanted coincidence that is occurring. Okay. So the sync tree does not contain any loops. So each packet will be delivered within a finite and maybe bounded number of hops. Okay. So here the links and routers can go back and forth. So different routers may have different ideas about this current topology. Okay. So here we acquire the information onto which base its sync tree will be computed and how it will be collecting the data. Okay, so sync tree and of course the optimal solution will definitely be the benchmark for this routing algorithm. So next is coin changing problem. Okay, so we'll be having an integer array of coins. Everything will be having a size of m. Okay, so here we'll be having different types of currency and the integer sum. Okay, so maybe if you have an infinite supply, okay, like sum is equal to 4, coins is equal to 1 2 3. Okay, so maybe you can go with 3 plus 1, that's one solution. Okay, or that's all, only one you'll be there. Okay, so maybe if you can go with the sum 4, okay, you can go with different possible means. Maybe 1 you can go with 4 times, okay, or maybe 1 2 times and then 2 1 time, okay, or maybe 2 you can go with 2 times, or maybe 1 and 3 one time. So these are the possibilities that you can produce the output is equal to 4. Okay, you understood? So sum is equal to 4, coins you have 1 2 3. What are the possibilities that you get sum is equal to 4? So how it will be? So 1 4 times, 2 2 times, uh, yes, 1 2 times and 2 1 time, or maybe 1 1 time, 3 1 time. So these are the possibilities. Okay. For example, sum is equal to 10, coins is equal to 2536. How you can obtain? Okay, so 2 5 times, 5 2 times, 2 2 times, 3 2 times, 2 2 times, 6 1 time, 2 1 time, 3 1 time, 5 1 time. Okay, so these are the ways. Okay, so that is how, even when I was doing my third or fourth standard, I used to have some color coins, and we used to do like this one. We had this problem during third or maybe fourth standard. We had this color, and even the teacher used to explain how you can add. Okay, so that is how it goes. Okay, so the above function will be computing the same sub problems again and again. So for the coins 1 2 3 and maybe n is equal to 5, so same thing you can go 3 2. Okay, you can go for. So maybe the function 1 3 you can call it 2 times even. Okay, so that is how it goes. So 1 2 times, 3 1 time, you get the total to be 5. Okay, or maybe 2 1 time, 3 1 time, you get the total to be 5. Okay, so if we draw this complete tree, okay, so 1 2 3 5, so that one you are going to split it up. Okay, so 1 2 3 2, 1 2 5. Okay, so that you are going to split it out. Okay, 1 2 3 5, so 1 2 3 2, 1 2 and then 5. Okay, so similarly everything you are going to split it out. Okay, so 1 2 3, okay, minus 1, 1 2 2, 1 2 3, 1 5. Okay, 1 2 0. So what are the numbers which doesn't have the possibility? You will have 0. Okay, the other one you will be adding out. Okay, so that how it is going. Okay, so either you can include or maybe you can exclude. Okay, so if we are the coins n minus 1, so maybe we can have instances of that coin unbounded inclusion. So you'll have coins n, some minus coins of n minus 1, and we move the coins n minus 2, and similarly we can't move back and we can't make any choices. So for the exclusion part, you'll have count coins n minus 1 sum. Okay, so finally you are going to add all the possible choices. Okay, so count coins n sum minus coins of n minus 1 plus count coins n minus 1 sum. Okay, so finally you are going to add them. So this is what you are going to have it in the program. Okay, so define count coins n comma sum. So if the sum is equal to 0, then return 1. If the sum is less than 0, no solution, so which means that return 0. If the n is less than or equal to 0, then return 0. Then you have the sum of the solution. So return count coins n minus 1 sum added with count coins n sum minus coins of n minus 1. Then finally you have the driver program coins 1 2 3. Okay, you find the length of the coins. Okay, so print count of coins n 4. Okay, so this is how, for example, 3 1 you can have, 2 2 you can have. Okay, so that is the possibility. So that is the reason you get the output to be 4. You know how the output is coming as 4? 4 is nothing but the number of possibilities. One possibility is 1 4 times. Second possibility is 2 2 times. 1 3. 4. So that is the way. Okay, right. So the time complexity order of 2 power sum and auxiliary space order of target. Okay, so this is what you have the overlapping subproblems, similar for especially for overlapping subproblems, and in order to find the optimal solution we'll go with this one. So you have to solve up even for the bottom up approach also. Okay, so you have to use the 2D vector to store the overlapping subproblems, and you have to traverse the whole array in order to find the solution and store it in the memorization table. So this is the dynamic programming, okay, approach for the coin changing problem. Define count, coins n comma sum. Table, you are going to store it in the memorization table, okay, in the bottom up manner. So 0 for x in range, for x in range sum plus 1, okay. So you have for I in the range of n, table 0 I equal to 1. Then you fill the rest of the table in the bottom up manner. So for I in the range 1 comma sum plus 1, for j in range of n, okay, and you count the solutions including the coins. So x is equal to table I minus coins of j if I of coins j is greater than or equal to 0. So else case you will have to return 0. Okay, then you count the solutions excluding the coins of j. First we included the coins of j, next we excluded the coins of j. So y is equal to table I j minus 1 if j greater than or equal to 1, else 0. Okay, so finally you return the table sum n minus 1, and finally you'll have this one. Okay, coins 1 2 3, n length of the coins. So here you'll have 4 possibilities. Okay, so I mean sum is equal to 4. Okay, so for this one you'll be having 4 possibilities. That is how you print the count of the coins n sum. So the output is equal to 4, and here for the bottom up approach, you'll have order m multiplied by sum and auxiliary space order m multiplied by sum.